Welcome to my channel. In this class, we will be going to discuss about fuel air cycles and their analysis. In IC engine, we have came to know about air standard cycles. As we know, the air standard cycles are highly hypothetical cycles which have no use in practical engines. So, according to practical running condition or working condition of an engine, we need to consider a different types of cycle. That is called actual cycle of the engine. This fuel air cycles is the analysis of actual case of actual study of working fluid whichever has been considered that in air standard cycle only air is the working fluid, but for fuel air cycle we will consider air plus fuel vapor mixture is working fluid. So there will be change in efficiency, change in work output. How? See, it has been seen by various experiments that air standard cycle efficiency is nearly about 56% of a highly qualified, highly designed engine. But it has been seen that after fuel air cycle analysis or actual cycle analysis, the efficiency has been reduced to only 28%. What does it mean? There will be a huge difference between work output of these two cycles. Let us analyze that. Why we need to study these fuel air cycles? As I have told you that air standard cycles have not actually any use in our daily life. In actual case, the engine working conditions are quite different. There are some assumptions to study the air standard cycle. In actual case, those assumptions does not hold good. That's why for our practical purpose, for practical working condition of engine, we need to study fuel air cycles. Now, what is the difference between these air standard cycles and fuel air cycles? As all of you know, in air standard cycle, the working fluid, that means in the cycle, whatever the fluid is working again and again, has been considered air only. We know air is an ideal gas. Air behaves like an ideal gas. So, whatever equation we have implied to analyze the air standard cycle is not actually true for actual case. Those equation will be changes. That means the graph will also change and work output and efficiency will be affected. So, to study the actual condition, we need to study fuel air cycle. In the fuel air cycle, the analysis has been done in very simplified way. In air standard cycle, the analysis cannot bring out the effect of air-fuel ratio on the thermal efficiency because working medium was assumed to be air. In this chapter, we will consider the presence of fuel in the cylinder is into account, and accordingly the working medium will be a mixture of fuel, vapor and air. By fuel air cycle analysis, it is possible to bring out the effect of fuel air ratio on thermal efficiency and also study how the peak pressure and temperature during the cycle will vary with respect to different fuel air ratio from the air standard cycles. In general, influence of many of engine operating variables on the pressure and temperature within the engine cylinder may be better understood by this fuel air cycle analysis. So this fuel air cycle analysis takes into account some crucial parameters. Those are the actual composition of cylinder gases, number one. Number two is the variation of specific heat with the temperature. Number three, the effect of dissociation. Number four, the variation in the number of molecules. So these are the four typical parameters based on which the fuel air cycle analysis has been done. Now before getting to the analysis, we need to consider some assumption first. Those assumptions you can see on the book IC Engine by V. Ganesan at page number 108. The assumptions are: number one, there is no chemical change in either fuel or air prior to combustion. What does it mean? That means before combustion or after combustion there will be no chemical change of the fuel or air. That means there will be same chemical constituent before combustion, and before combustion there will be no change of chemical composition, and after combustion also, after burning of the fuel also, the burned gas will not change its chemical composition. Number two, subsequent to combustion the charge is always in chemical equilibrium. That means before combustion and after combustion, whatever charge has been introduced inside the engine will be always in chemical equilibrium. What does it mean? It means the charge will not interact any chemical reaction. Number three, there is no heat exchange between the gases and the cylinder walls in any process. They are adiabatic. This is very crucial assumption. This assumption has been taken in air standard cycles also, that during expansion and compression stroke, or you can say all over the cycle, there will be no heat exchange between cylinder wall and outside atmosphere. So no heat flow inside or outside of the engine cylinder. So we can consider the cylinder wall are adiabatic wall. Number four, in case of reciprocating engines, it is assumed that the fluid motion can be ignored inside the cylinder. So if we consider there will be fluid motion, the pressure may vary, so we will consider the fluid motion inside the cylinder, though there will be swelling effect, is zero, there will be no motion of the fluid. Number five, the fuel introduced with the air is completely vaporized and perfectly mixed up with the air. What does it mean? That means there will be a homogeneous mixture will be created with the fuel vapor and air. Number 6, the burning takes place instantaneously at top dead center or at constant volume for Otto cycle or SI engine. This assumption is only for Otto cycle. Now, all this assumption has been taken for the analysis of fuel air cycle. Some of this analysis, apart from these 5, is also there in air standard cycle analysis. Only the change is in air standard cycle we have considered the working fluid is only air. In this case we will consider fuel air mixture is working fluid of the cycle, because we know in actual engine there will be not only air as working fluid because we need to introduce fuel for heat addition, so there will be fuel plus air mixture as working fluid, and products will be created after burning accordingly. So let us see the analysis. First of all, composition of cylinder gases. What is composition of cylinder gases? As we know, the air fuel ratio changes during the engine operation. Typically, there are three types of air fuel ratio. One is lean, another is stoichiometric, another is rich. In lean mixture, the amount of fuel present in the mixture is less than the quantity of air. That means quantity of oxygen. What does it mean? It means whatever oxygen is required to burn all the fuel present in the mixture is more than sufficient. So that type of mixture is called lean mixture. Now what is stoichiometric? The amount of oxygen present in the mixture is well enough to burn all the fuel. That means this mixture have proportionate amount of fuel and oxygen quantity. And what is rich mixture? In rich mixture, the amount of oxygen present in the mixture to burn all the fuel is less. That means there will be in richer mixture, in rich mixture, there will be unburned fuel. Because of less amount of oxygen, some amount of fuel cannot be burned. That is called unburned fuel. So, depending upon engine operations, we need to change this fuel air ratio. That means at the starting, when the engine will be a cool down situation, we need to heat it up. We will send more fuel. That means we will send rich mixture. So when it will just running condition, we will send lean mixture, because in no load condition there will be no required of sending much more fuel, because work output needed is very less. We need to just run the engine, and for full load condition we will send generally the stoichiometric mixture. This change in air fuel ratio affects the composition of gases before composition as well as after combustion. Particularly, the percentage of carbon dioxide, carbon monoxide, water vapor, etc. in the exhaust gases. So, composition of cylinder gases depend upon types of fuel mixture we are using according to running condition of the engine. In 4-stroke engine, fresh charge as it enters the engine cylinder comes into contact with the burnt gas left in the clearance space in the previous cycle. Now, this amount of the burnt gas in this clearance space will vary upon engine speed. If engine speed increases, the amount of burnt gas will increases inside this clearance space. Why? Because as we know, scavenging process, that means whenever we will open simultaneously these both at inlet valve, the scavenging process will occur when the piston will be at top dead center at the intermediate section of the two cycle. Okay, so scavenging process needs some time. We need to give some time to the engine to completely wash out or to partially wash out of the burnt gas of previous cycle. So when the engine speed will be much more higher, we are not giving that much time to the engine for the scavenging process. So if engine speed increases, the burnt gas inside the clearance volume will increase. And if burn gas will increase, it will dilute the phase charge. Whenever the phase charge will introduce from the inlet valve, this burned gas, which will be at high temperature, it will get expanded and occupy the vacuum space, and it will restrict the phase charge introduction. Thus it will dilute the phase charge or air. So as the engine speed will decrease, the scavenging process will get time. That means by the phase charge, the burn gas will wash out at the atmosphere, and this amount of burn gas will reduces, and phase charge will not diluted in that manner. So there will be increase of oxygen quantity, because there will be increase of amount of air, density of air. Okay. So as we know, oxygen quantity is a crucial thing for burning the fuel. So whenever there will be introduction air plus fuel vapor, if oxygen quantity decreases, we cannot burn all the fuel. There will be some amount of fuel which will be unburned. So this unburned fuel is our direct heat loss. So if engine speed increases, the amount of burn gas inside the cylinder will increases, and that will dilute the phase charge. That means decrease the oxygen quantity, and it will decrease the work output of the engine. Thus efficiency of the engine will decreases. Okay. So composition of cylinder gas, how this parameter is affecting fuel air cycle, that means actual condition of the engine, we have understood. Now next parameter is our variable specific heats. As we know, all gases except monoatomic gases show an increase in specific heat with temperature. The increase in specific heat does not follow any particular law. However, over temperature range generally encountered for gases in heat engine 300 K to 2000 K, the specific heat curve is nearly a straight line, which may be approximately expressed as Cp equal to A1 plus K1T, Cv equal to P1 plus K1T. At higher temperature, above 1500, it will be not linear, it will be abruptly changes, there will be a curve. So Cp in that case will be 1 plus K1T plus K2T square. Cv will be B1 plus K1T plus K2T square. Now all of you know what is specific heat. Specific heat is amount of heat required to increase 1 degree temperature of the substance. Now as I have told you, all the gases, the specific heat will increase with increase the temperature. So that it will affect the efficiency of the engine. How? Let us see. As I have described, the value of Cp and Cv, that means specific heat at constant pressure and specific heat at constant volume, is follow linear equation and curve equation at different temperature. But they have difference. The constant R will be always same. R will be always constant. See, R in both case is A1 minus B1. Now look at this process. Suppose we have considered value of Cp initially, say first case was 2. Now it becomes, after increase of temperature, the specific heat of at constant pressure has been increased and it becomes 3. Say 3, suppose it becomes 3. And value of Cv initially was 1 and it becomes 2 after increase of temperature. Okay, and we are increasing these values in such a way that Cp minus Cv, that means R is always same, always constant. See, in this case Cp minus Cv are equal to 1 in first case. In this case also Cp minus Cv R is equal to 1. So R is always constant. So no problem in this assumption. Now we know the value of gamma, which is equal to Cp by Cv, in first case was 2 by 1 is 2. In second case 3 by 2, that means 1.5. So as specific heat increases, the value of gamma decreases from 2 to 1.5. Okay, because R is always constant. We are keeping this gap. Always constant. That's why this gamma will decreases with the increase of the value of Cp and Cv. Now to analyze any cycle, say this is a PV diagram of an Otto cycle. We are taking an Otto cycle for our analysis. So 1, 2, 3, 4 is our Otto cycle, air standard Otto cycle. In this air standard Otto cycle, we know 1 to 2 and 3 to 4 is our adiabatic process. For these two process, we know Pv to the power gamma equal to constant, and for any process Pv equal to RT. Now we are replacing this P by this P equal to RT by P. We are getting an equation T into V to the power gamma minus 1 equal to constant. So from 1 to 2 process, this compression process and expansion process, 3 to 4 process, will follow this equation T V to the power gamma minus 1 equal to constant. But as we know, when the temperature will increase, the specific heat will not constant. It will be variable. It will be changed. How it will be changed? With the increase of temperature, the specific heat also increase. So if the specific heats will increase, the value of gamma will decrease. So if we consider the variable specific heat in fuel air cycle in actual condition, this equation will not be followed. Whatever in air standard cycle we have considered will not be followed. So there will be a new equation, say T V to the power K minus 1. K we are writing instead of gamma because gamma is decreasing in this case. So T V to the power K minus 1 equal to constant. Okay. So this is our new equation which will followed by our engine. Now look at this graph. In this graph 1 to 2 was our compression process. As we know, during compression volume will decrease and temperature will increase. So as soon as the temperature increases, these specific heats will also change. It will increase also. So the graph will not follow this line anymore. It will follow a line below this line because our equation has been changed. Our exponential constant has been changed. It is decreases. So our graph should be below than previous air standard line. So our line will be 1 to 2 dashed. In our new case, in actual case, say 2 dash was here. Now from here we will add heat into the cycle. 2 to 3 was our constant volume heat addition in a standard cycle. Now suppose to increase the pressure from 2 to 3 or increase the temperature from 2 to 3, we are adding 100 kilojoule of heat. Previously in air standard cycle, we are adding this much heat. Now, specific heat of the cycle has been increases. As we know, specific heat is the heat quantity required to increase 1 degree temperature. That means now this 100 kilojoule will not be enough, will not be sufficient to increase. This 100 kilojoule heat will not be enough to increase the same amount of temperature, because with the variable specific heat, more heat is required to increase 1 degree temperature of the system, because specific heat is increasing. That means much more heat is required for this improvement. So for same heat input, there will be less amount of temperature and pressure generation. So instead of 0.3, it will reach up to 3 dash. Okay. Now, whenever we will try to expand from this point with constant specific heat, it will follow a line parallel to this line, because specific heat not changing. Now, if we follow again variable specific heat, it will follow a line like this. It will starting deviating from this point gradually, because as the temperature is decreasing from 3 to 4, as the temperature is decreasing, the specific heat will also decrease. So temperature fall down will not be that much, because specific heat is decreasing. That means heat required to increase the temperature is decreasing. That means for same heat, it will reach up to a greater amount of temperature and pressure. Say that it will be 4 dash, and then there will be heat reduction from 4 dash to 1. So this is our typical cycle if we consider variable specific heat of the engine, whenever we will consider the working fluid as fuel and air mixture. That means a gas. So from this graph we can see easily the 1, 2, 3, 4 was our net work output, because PV diagram shows our work output, net work output. Now due to variable specific heat, our new work output becomes, net work output becomes 1, 2 dash, 3 dash, 4 dash. So from this graph we clearly see now our net work output is this much. So this portion of the work has been diminished. In this analysis, we can see this portion of work is not actually was there, whatever we have considered in air standard cycle. So there will be less amount of work output whenever we will consider actual condition and variable specific heats of fuel air cycle analysis, and efficiency thus of efficiency of the system will decreases. Okay. Our next consideration for fuel air cycle analysis is dissociation. What is dissociation? Dissociation is the process can be considered as the disintegration of combustion products at high temperature. Dissociation can also be looked as a reverse process of combustion. During dissociation, the heat will be absorbed, whereas during combustion, the heat will be liberated. In IC engine, mainly dissociation of CO2 into CO and O2 occurs, whereas very little dissociation of H2O into H2 plus O2 will also occur. See, at 1000 degrees centigrade, the CO2 molecule basically breaks into CO and O2 molecules and takes some heat. The CO2 takes some heat and breaks into CO and O2 molecules. At 1300 degrees centigrade, the H2O molecules take some heat and break into H2 and O2 molecule. So whenever there will be some dissociation at high temperature, these molecules, this product will break into other molecules and it will take some heat inside. What does it mean? Whatever heat we are adding in the cycle, that will be reduced by this dissociation process. Now, when the mixture will be rich, there will be present of CO molecules and O2 in the mixture. Okay, at richer mixture there will be already CO and we know in air there will be O2. This present of the CO and O2 molecules will prevent the dissociation. Actually, what will occur, already present of the CO and O2 molecule, it will reassociate and this reaction will happen in opposite direction and reassociate into CO2. So in that case, this presence of CO and O2 molecules will prevent the dissociation actually. So there will be no reduction of heat in the richer mixture. As we know, there are three types of mixture: lean, stoichiometric and rich. On the basis of this, we will analyze our dissociation. We know what is lean mixture. The amount of oxygen present is much more than amount of fuel to burn all the fuel. Stoichiometric means the amount of oxygen present in the mixture is sufficient enough to burn the fuel, all the fuel. And rich mixture is amount of oxygen present in the mixture is less than the amount of oxygen required to burn all the fuel. Though these three types of mixture, in these three types of mixture, in lean mixture, we know in lean mixture amount of fuel is less, so there will be no sufficient amount of heat generation to occur this dissociation. So dissociation generally does not occur at lean mixture. Now next, stoichiometric mixture. In stoichiometric mixture, there will be maximum dissociation. Why? Because the amount of air or oxygen is present to sufficient burn all the fuel, so all the fuel will get burned. So maximum temperature rise will occur in the system. So that temperature rise will dissociate the product CO2 and H2 into other molecule and take some heat from the system and reduce the pressure, peak pressure and temperature of the system. Now as you know, in rich mixture there will be already present of CO and O2 molecules. So the rich mixture will also prevent the dissociation and this reaction is generally occur in opposite direction. Now look into this graph. This graph is drawn in terms of temperature versus mixture type. In mid section is stoichiometric line has been shown. This is stoichiometric. This is stoichiometric line. Below stoichiometric lean mixture, above stoichiometric the mixture is rich. Now as the mixture is very lean, there will be that no sufficient amount of heat creation, so there will be no dissociation occur. As the mixture gets towards stoichiometric, there will be creation of heat or production of heat that will create the dissociation. So dissociation will occur as the mixture is getting towards stoichiometric. Now at stoichiometric, the maximum dissociation will occur, and towards the richer mixture there will be no dissociation because already present of CO molecules will prevent the dissociation. So this dotted line is our curve which shows when there will be no dissociation. This line is thick line is so when there will be dissociation of the system. See, in linear mixture, when the mixture is very lean, there will be no dissociation. As the mixture is getting stoichiometric to a stoichiometric, it will dissociate, and temperature rise will not that much, it will fall down. At the mixture getting towards stoichiometric, the temperature difference is much more than no dissociation. But it has been seen practically that just above the stoichiometric line, the maximum temperature rise will occur and maximum dissociation will occur. As the mixture getting researched, these two lines is again converging, and at very rich mixture there will be no mixture because there will be a huge number of CO molecule will be present in the system. The effect of dissociation on power output for a typical 4-stroke engine operating at constant speed has been described in this curve. You can see in this curve, if there will be no dissociation, the brake output is maximum when the mixture ratio is stoichiometric. The shaded area between brake power graph shows the loss of power due to dissociation. When the mixture is quite lean, there will be no dissociation. As the fuel air ratio decreases, the mixture becomes rich. The maximum temperature rise and dissociation commence slowly. The maximum dissociation occur at chemically correct or stoichiometric mixture. Stoichiometric means chemically correct mixture. As the mixture became richer, the dissociation effect tend to decline due to incomplete combustion. Now, due to dissociation, there will be temperature fall of the system. See, suppose we have expanded from this 3' point. Now, with the dissociation, some amount of heat will be consumed by the CO2 molecule to break into CO and O2 molecule, or H2 molecule to break into H2 and O2 molecule. So heat will be absorbed, some amount of heat will be absorbed, and the temperature rise after the expansion, at the end of expansion, will not that much, will be below that point, say 4 double dashed. Now for richer mixture, the molecules, the CO and O2 present of CO and O2 molecule reassociate and it liberates some heat, and if reassociation occur, this expansion process will reach up to 0.4 dash. So from this curve, effect of dissociation we can understand in PV diagram. If dissociation will occur, there will be loss of heat and the curve will go below the air standard line. Thus, it will reducing the work output. This much work output had been reduces. The net work output is now area under this curve 1, 2, 3 dash 4 double dashed. So work output will be less with the dissociation. So efficiency of the system will also decreases. Now our next point is effect of number of moles. As already mentioned, the number of molecules present in the cylinder after combustion depends upon the fuel air ratio, type and extent of reaction in the cylinder. According to Glass law, we know PV equal to nRT. The pressure depends on the number of molecules or moles present. This has direct effect on amount of work the cylinder gases can impart on the piston. That means if number of moles increases, after heat addition the temperature rise will increase much more and peak pressure rise will also increase much more. That means if number of moles increases in the cylinder gases, this curve will be, this area under the work output curve will be much more because peak pressure rise will be much more. Now if number of moles is less, this peak pressure rise will be less. So this number of moles is directly affect the work output of the engine and efficiency of the engine. Thank you for today. We will next discuss the actual cycle analysis of IC engine. Thank you.